Hello everyone, and welcome back to a new video in our introduction to the finite element method, in which we are basically going to show an example on finding the stiffness matrix using the isoparametric formulation for a quad element. Now, of course, in case you're wondering, we are following the book, a first course in the finite element method by Dariel and Logan, and this is basically the ultimate part of a multi-part series on the finite element method that is going to be linked on the top right. Now this is going to be basically the finalization of this entire thing. Usually all the finite element courses being taught online or at campus end when the isoparametric formulation has been reached, and I want to end it on this note. Of course, I might even want to show some written examples and solved examples, but I will no longer explain any theory after this presentation. I hope that you enjoyed it so far. I might in the future, like one time, just double check something called the bending element, but that is for the future. For now, I think that this would finalize the new stuff that you would learn in the finite element method series, and I hope that you enjoyed it. Of course, the viewer, feel free to suggest any advanced methods you want me to cover. I might cover this in the future whenever I have some time. Anyway, we're going to check out an example today to try to find the stiffness matrix using the isoparametric formulation. So without further ado, sit back, relax, and enjoy the show. Alright, so here I have an element that is being discretized into two quads. The quads are 25 by 25 millimeters each and 10 millimeter in thickness, so this is a rather small piece. We can disregard the forces for now. I just put them for show. You could go one step further and use the forces to find the displacement or the stresses, something that you can find in the book Dariel and Logan. For now, here, our main goal is to find the stiffness matrix of this assembly using the isoparametric formulation. For the isoparametric formulation, just to remind you, I want to go a little bit further down. This is the thing that we use to find the stiffness matrix using the isoparametric formulation. Please notice that I have covered this in previous videos, and I will be linking the most recent video in the top right. So here, our main goal is to find the stiffness matrix by double integrating ST domain and converting it to the XY domain. Now to do this, we have to assemble something called the strain displacement matrix, and this is a function SNT. So we need to evaluate B as a function of SNT, which further requires J as a function of SNT. And because we are using the Gauss quadrature, we are going to apply 4 points as a summation in order to evaluate the integral. So what we are going to do is we are going to start a loop, and you would have the SNT coordinates, and some books call them Xi and Eta with their weights, and you would have to zero the stiffness matrix, meaning that you would have to initialize it, and now you are going to sum up this entire thing, because you are going to approximate the integration numerically by using Gauss quadrature. Gauss quadrature, just double check the previous video, is simply the evaluation of the integral by means of function multiplied by weight, and the weights for those points is 1. This, of course, introduces some numerical approximations, and that is totally fine, and that's the reason why you have mesh sizing in a robot, for example, and why mesh sizes affect the answer that you get from your structure. So you would have to initialize your stiffness matrix, go over all the 4 points, find those stuff, add those stuff, and rinse and repeat. I want to mention that discretizing this element into 2 pieces might be not really good. You would need more pieces to discretize the element to capture its bending behavior or axial behavior. However, to make it humanly possible to explain, I am discretizing it into 2 elements rather than 16 or something. So let's dive into it. To start with, I am going to take element number 1, which is on the left side. This is the left quad. Now, element number 1 is basically between node 1, node 2, node 3, and node 4. And you know the drill. We need to first of all prepare the Jacobian matrix. This means I would need the coordinate vector for for x and the coordinate vector for y. I noticed something wrong, and I want to give a disclaimer. I want to give a very quick warning here. I read the book first course in the finite element method, and I don't know, but it seems that the J matrix that the book is suggesting, the book Dariel and Logan, the J matrix that he is suggesting seems to be odd. I need to double check that. Like, I compared it with all the PhD stuff I have, and I thought that it seems to be fishy, so I need to double check that. I'm using an alternative version for the J matrix because I kind of started doubting the J matrix in the book, and I will raise this concern to Professor Daniel Logan. I will send an email to him. However, I've used an alternative version which I kind of know. B here represents your T, and A here represents your S. So this should, in theory, give the exact same Jacobian as in Daniel Logan's book. And I've tested it on his example, and it turned out to have identical results. So I'm not really sure. I need to double check with the book again because the J that is written in the book seems to have some problems. So in order to do that, I need, of course, the X's and the Y's. And this would, of course, lead us to prepare the B matrix. The B matrix, as the book Daniel Logan suggests, needs you to calculate A, B, C, D, which are some constants. Not really constants, are functions in S and T, which I have evaluated here for the given coordinates. And then, of course, use it to evaluate B matrix here, because the B matrix needs the derivatives of all the shape functions. Now, just to remind you, I have written here the shape functions, and then I further proceed to derive or to partial derive each shape function with S and T, because I would need those here. So the partial derivatives of all the shape functions is found here, something that is not mentioned in the book. So you feel free to take them if you want, or derive them yourself. Alright, so now we are almost ready to find the stiffness matrix, and for that I enlisted the help of MATLAB. So, well, I just want to go through the code very quickly. I have some functions in MATLAB programmed to find the various things. The first thing is to find the local K, or the local stiffness matrix. To find the local stiffness matrix, you need to input the coordinates in X, the coordinates in Y, the thickness of the plate, the elastic modulus, and the Poisson's ratio. Those Gauss points are exactly the same. Those are positive negative 0.5773 for S and T with weights of 1. The beauty of using 1 over square root 3 is that the weights are 1. So you just have to sum up the integrations. The part of Wi and Wj is going to be 1s. Then we proceed to calculate the D matrix. This is done outside the loop because it's something that doesn't change, so I want to spare some calculation effort. There is a function I will show you which finds the D matrix. The D matrix is basically the material matrix. Then the local stiffness matrix is initialized 0 is 8 by 8 because I have a quad with 4 nodes, each node able to move 2 directions. Now we cycle through the Gauss points from 1 to the number of Gauss points. We get to the S of the Gauss point, we get to the T of the Gauss point, we get to the W of the Gauss point. Then we find the J corresponding to the S and T we have. We find the determinant of the Jacobian matrix, find B, and add to the stiffness matrix. Those steps, J to K, are what you see 1, here, and here. This step, Jacobian, is part of this. This determinant is also part of this. This B matrix is also part of this. And this is basically those 2 steps are combined. Of course, the getting of S and T is what you find here. Do 1 to 4 is what you get here from the for loop. Now, programming languages like MATLAB and Python are very important in case you want to seek PG studies or postgraduate studies whilst having some interest in the finite element method or in simulation in general. For the Jacobian, this is the implementation that I have shown to you. It's a one-line implementation. This is the implementation I have shown to you in the slide. This is the Daniel Logan implementation, but when I case tested it, I did not get the same values as in his example, so I kind of doubt that. I'm not sure if that is right or wrong. So I chose a different one from another reference. Now this, of course, calculates Jacobian matrix. You need S, T, coordinates X, coordinates Y, which is as you see. Then you need to find the D matrix. D matrix is just a material matrix. It's 1, new, 1, and whatever. This is the stuff that we have learned in our first 2D problem, which was I think it was called the constant strain triangle. I will put a link on the top right. And of course, the final MATLAB implementation file that we need is the B matrix. And yeah, it's basically this. You can see the A, B, C, D according to Daniel Logan's book. You can see the derivative of all the shape functions with respect to S and T. We establish our B's, and then of course we don't forget to divide by determinant J. to find the B matrix itself. This all is packed into a nice, neat MATLAB script that can find the stiffness matrix of any element that you want. You can just say the elastic modulus, the mu, and all those inputs, and you run this thing and you get the local stiffness matrix, something that you see here. Now this script is run for the first element and run for the second element. And now the question is, how do I find my global stiffness matrix? This is where the assembly theme comes yet again into play, and it's a headache. Allow me to show you. Like, this is at least the best I can do in terms of trying to show you what I will do. This is the stiffness matrix of element number 1. This is the stiffness matrix of element number 2. And no, that's not a typo. They are identical in terms of numbers. And now the assembly begins. You need to understand that element number 1 connects node 1 with 2, with 3, and with 4, meaning that the degrees of freedom that the stiffness matrix represents is U1, V1, U2, V2, U3, V3, U4, V4. For element number 2, it connects 2 with 5, with 6, with 3, and this means that your degrees of freedom are U2, V2, U5, V5, U6, V6, and U3, V3. Now this becomes a really hard thing to do manually, because now, okay, this is for example U2 and V2 with U2 and V2, and you have here U2 with V2 and U2 with V2. So you need to group them and add them together. I tried to give some color coding for this, like the red box goes with the red box. I don't know what this color is, goes with this color. The yellow box goes with the yellow box, and the green box goes with the green box. Also, there are some extra things that exist in element number 2 but don't exist in element number 1. I've colored them in magenta, whatever that color is. And to be able to see how it works, I showed to you this in glorious form. You can see each of those boxes, how it affects the stiffness matrix in various terms. And you can see that there are some zeros. Those zeros means that there is no connection between the two degrees of freedom. For example, take a look at those zeros, those 4 zeros. Those 4 zeros are the degree of freedom 1 with a degree of freedom 5. This is 1, that's 5. They don't see each other, they don't feel each other, there is no direct connection between them, because there is no element connecting between them. However, also 1 and 6, also 4 and 5, also 4 and 6. You will notice those zeros that make sense because there is no connection between the degrees of freedom that are in question here. Fantastic. Now here, of course, the end is nearing, because now all you have to do is this is the stiffness matrix you have to solve. I put here some supporting conditions, meaning there is no movement in U and there is no movement in V for node number 1 and node number 4, meaning that you're going to slash and dash the U1, V2, V1, U4, V4 in both lines. Of course, you have force matrix, you would have to slash and dash those two things for U1, V1, and this is U2, V2, U3, V3, and U4, V4. And the resulting is something you can solve. You have the simplified condensed K matrix, the condensed force matrix, which means you get a displacement. Of course, the displacement is ridiculously small. The reason behind this is because I have a steel plate with 100 Newton force. This is nothing in comparison, but yeah, well, it is what it is. This is the original plate in red. Let's take a look at the displacements that happened. So I'm going to exaggerate now. Those are not to scale. So let's take a look. Now for 1 and 4, nothing changed because those are pinned. Now this is displacement of node number 2. You see a negative displacement in X, like this, and a negative displacement in Y, like this. So this is the new node number 2. This is the new node number 2 after the displacement. What about node number 3? Node number 3 seems to move into the positive X and move down a little bit. So you can see this is node number 3. Okay, fantastic. I can see some bending action here. Then I notice that node number 2 goes back despite the 100 because of the bending action, which kind of makes sense to me so far. Now this is for 5 because 4 is zeros. For 5 goes even further. I mean, look, compared. 5 goes even more inside, and it goes even more down. So that's 5, okay? And for 6, it goes even more positively and more down. So something like that. Yep, that is what I was expecting for a beam under bending. Of course, this deflection seems to make sense. You could still calculate some stresses. However, those displacements are of course not accurate because my mesh is big. You could discretize more and have a more accurate mesh. So anyway, this as a full example for the isoparametric formulation. I hope that you enjoyed. With that being said, I think that my finite element method series is going to an end. It's closing in. So this was a very long journey. It's almost 27 episodes. Like, wow, this is one of the longest running episode series in the channel. With that being said, I'm really thankful for having you around me. Feel free to ask any questions with regard to finite element in general or on the isoparametric formulation itself. I will do my best to answer them. Usually I answer within 48 hours, sometimes a bit more, but I'm quite responsive in the comment section. And with that being said, I want to give a final finite element method sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time with a certain quality I try to achieve, and for that I am forever thankful. As per usual, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing as a sacrifice to the YouTube algorithm, helping me to increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.